Okay, welcome everyone to my continuation of what is algebraic graph theory. We are still in the world of matroids, and we are going to explore greedy algorithms because I personally feel like this is the whole point about matroids. And today I make it a little bit more precise. So greedy for matroids. So we'll see what that means. Again, greedy algorithms. I will show you some examples. Obviously, you don't need to remember everything you have done. Greedy algorithms, fantastic, absolutely great. And matroids are essentially the perfect object to study greedy algorithms. Not quite. I will talk about that in a different video. But for now, it's kind of, you could think of them as being kind of the perfect setting to study greedy algorithms. Okay, so let's get going, I guess. So greedy strategy for spanning forests. You have a graph and you want to find spanning forest in that graph. And you can do that with a greedy algorithm. Essentially, it goes as follows. You pick an edge, any random edge, pick another random edge, you pick another random edge. You just always pick some edge locally, and the only thing you need to check is that you don't run into cycles. So you never pick an edge where you would create a cycle. So you will never pick this edge 12 here, for example, because you've already chosen those. Okay, and turns out that this actually works. And turns out that this is really insane in some sense, because this works weighted as well. So we can also find the maximal spanning forests. A bit annoying, my example here above finds the minimal spanning forest, not the maximal one. We'll see later that this is actually completely the same. Doesn't really matter which one you're searching for. So let's just go for it. Just keep in mind that I'm saying maximal because my theorem will be formulated for maximal, but that doesn't really matter. You can also find minimal. There's some kind of the symmetry operation that exchanges the two. But anyway, so how do we do that? Well, we want to find not just any spanning forest, but a maximum spanning forest, or sorry, a minimal in this case, because in my example, I will find the minimal one. So how does it work? You just pick the edge with it. So everything is weighted, and I want the spanning forest so that the sum of the weights, so the weights are just the numbers above here, and the sum of the weights is minimal. And how does it work? I just pick the edge. This is probably a bad color. I just pick the edge with the minimal label. Okay, and I pick the edge with the next minimal label. And I pick the edge with the next minimal label. And I pick the edge with the next minimal label. I just pick the edges by, I just order the edges by their label and always pick one. That's greedy. I just always pick the smallest, right? A local strategy, it's a local strategy, and it will give me a global result. The only kind of constraint I have is that I, of course, do not want to create any cycles. So the only constraint is you do not pick an edge if it would give you a cycle. And turns out that this gives you the minimal spanning tree. So in the end, you would get this one here, for example. And this is kind of ridiculous. You kind of locally always do the one that is that looks best. Just take the smallest edge, the smallest weight on the edge, and just keep on going. Always take the smallest, and it works. It's just absolutely ridiculous. And kind of the point is that this is not a coincidence that this works, because we have already seen here spanning forest. It's kind of a basis of a matroid. So maybe for a matroid you can do something, and yeah, you can. And here's another greedy strategy, which is just really fantastic. So the one on the previous slide was for spanning forests, and that's the graphic matroids. And the one on this slide is for bipartite matchings, and this is a transversal matroid. Anyway, this is roughly how it works. So let's say you are a restaurant and you want to hire some person. So maybe you need a cook, maybe you need let's do it this way. Maybe you need a food taster, and maybe you need a kitchen cleaner. Fine. And let's say you have 5 applicants, A, B, C, D, E, and you can give them ranks. So you give them weightings, and that's exactly the weighting here. So you give them grades, like this one is good, this one is not so good. Let's say from 1 to 5. And you want to find the matching, the maximal matching. So you want to assign, and the graph encodes which, so A is only suitable as a cook, D is suitable as a cook, as a food taster, as a kitchen cleaner, and so on. So that graph somehow encodes how to, or has applied as a cook or cook, food taster, or kitchen cleaner, whatever. But this graph encodes, and you want to pick the graph such that you get all the jobs with the maximal weighting for the candidates. And you do it as follows. It's a greedy algorithm. So you just look at the numbers. So C is perfect. So whoop, C gets to be the food taster. Maybe I should just do this like this. C gets to be the food taster. 5 is the biggest. Then you take 4 as the second biggest. So B gets to be the food taster as well, but it doesn't quite work, as you can see, because C is already the food taster. Okay, so you go back and take the next one. So this one will be, oh, maybe I should put this here in green actually. So the next one is 3, and 3, yeah, good. E will be the kitchen cleaner. The next one is one of the ones, and now it doesn't matter. So let's just say A will be the cook. And all I've done, and this is the perfect matching, so a perfectly weighted matching, the maximal one. And all I've done is I've read through the list, just this is the best one, I assign it the job. This is the next best one, I assign it the job. Oh, didn't quite work because the job was already taken, so I drop it. But then I just go through the list, and this finds me, in this case, a maximal matching, which is kind of weird. Again, the naive strategy works. Can't be a coincidence, right? There's a completely naive strategy. Always do the maximal one first. And yeah, so this is again a matroid optimization problem. And turns out this is true for any matroid and any weighting function on the matroid. So the weighting function is just to assign ranks to your whatever, to the applicants. Okay. So for every weighting function and for every matroid, the greedy algorithm works. The greedy algorithm is just order the elements by their ranking and always take the biggest one that is accessible. This is written down here in more formal mass, but actually what is really written is just what I said, order them, or what I did in the previous examples, order them by their ranks and just take always the biggest one, or the maximal one that is accessible. And this works for absolutely every matroid and absolutely every weighting, which is just ridiculous. So in some sense, this really justifies the definition of a matroid. Because as soon as you show that your problem is a matroid, you're good. The greedy algorithm will solve the most crucial problems for you. And this is just, I personally feel like this is the point of matroids. And in some sense, yeah. So the complete statement is exactly what I just said. So the greedy algorithm works for all matroids and all weightings. And maximal and minimal is exactly the same. So I also did the maximal one here, and you get a maximal spanning tree. So maximal and minimal are kind of problems that are related by just sending A to A. Anyway, and it's actually even better, not just that this works, which is obviously the point I'm trying to sell here, but also you can somewhat characterize when a greedy strategy works and what pops out. So I will do that in the next video and very briefly on the next slide. And what pops out is essentially a matroid. It's not quite a matroid. We need something a little bit more general, which is a bit annoying to write down. It's called a matroid embedding. But anyway, we could think of being a matroid as almost a perfect characterization of when a greedy strategy applies, which is absolutely fantastic because greedy strategies kind of really easy and solve your problem kind of extremely efficiently. And this is an example that is not related to a matroid, and you really need this matroid embedding. So getting change, I had that in the previous video. So getting change is really, using the minimal number of points for change. Let's say you need 36. And what you do is kind of the greedy algorithm, you take the biggest one that is 3, 20, you take the next biggest one that fits inside 10, you then take the next biggest one that fits inside 5, and so on. And you never run into any problems. And this is a perfectly legal greedy strategy. Turns out that this one is not related to a matroid. So very often greedy strategies come from a matroid, but not all of them. And you can somehow fix that by making it a bit more general. And what you get is a matroid embedding. But I will postpone a more formal discussion to the next video, where I actually will kind of use an intermediate notion. So the notion of a matroid embedding is a bit painful to write down. Anyway, you could think of it as being kind of a generalization of a matroid. So the whole point of matroids, I say it again, I know I sound like a broken record, but no matter what, I will say it again anyway. Well, you can turn off the video, I guess, or the sound or whatever. But anyway, the point of matroids is the greedy algorithm. And it turns out that up to some fluctuations, the greedy algorithm applies exactly when you have a matroid around, which I think is pretty cool. Anyway, I hope you enjoyed this video, and I will hope to see you next time.